Connor is allergic to chocolate. CAC. The CAC team. CAC team. Yeah, CAC. Okay, Ronald McDonald. All right. Okay, so I suppose as you get to do your naming, etc., as you've noticed, so the reason I was absent last Thursday, was that I was involved in a workshop, to improve myself and be able to better serve you. And what I was doing in class previously, the groups of two and the questions, etc., that's a technique that I had read about called active learning. Although many hate it, but research shows that it actually works. So although, I may get bad recommendations from you, bad reviews from you, I'd rather that you learn than, not learn something. So now what I'm doing here is I'm taking this active learning to the next level. Okay, I want to formalize the environment. We communicate with each other, and you guys communicate together. There will be more fun things also kind of showing up in the class. And many have been asking me if I was going to commit to the flipped classroom based on feedback, and that was expected because also research shows it, that no one half the class typically wants to do flipped classroom, half doesn't, and I got 60% of you want to do the flipped classroom, 40% or not. So I'm not going to do the flipped classroom, but what I'm going to do, I'm going to turn this class into a lecture/lab, okay? And so you will be working actively in groups. It will slow down things a little bit, so we may not cover as much material as I'd like to, but my hope is that as you build up knowledge and experience, we can cover material faster as we hit the end of the semester, okay? I'm distributing some cool candy, good candy. This is good quality candy. They were on sale at Smith, so I grabbed a few bags, They're not chewed upon because I hid them from my son, so those are legitimate stuff. Okay, and also because homework 4 was apparently devastating to many of you. Okay. Now, you saw a couple of announcements come out this week, yesterday. So as we go through the semester, homework is going to get relatively easier, okay, because I'll be giving you more code than I used to. And that code is essentially just boilerplate. Import NumPy, do this and do that, okay, and then fill in the gaps. If you are very comfortable with programming, don't adopt my suggestions. You will not be graded on the homework, on the programming, sorry. You'll be graded on the homework. You'll not be graded on the programming. However, I will hold you accountable on the answer. So the more I give you, the more I expect back from you, okay? But that also means that you will not get partial credit on homework, no questions asked. Because homework is a real-life situation. As an engineer, at some point in your life, you're gonna be striving to get the right answer, okay? And in a controlled environment, if you can't get the right answer, I will not be helping you. Yes, Eric?
We did the whole homework, and we have the whole thing done, but we had like one typo, we get the slightly wrong.
Well, so let me clarify. If you have 10 steps in the homework and you miss the last step, you lose credit on that last step. Although even if you typed it correctly, okay? But on exams, you're going to get as much partial credit as possible, essentially, okay? Now, the questions in the homework are also going to change in character because I will be trying to push more towards critical thinking. So here's data. Interpret this data, give me some insight. And that is relatively an open question. So as long as you interpret it reasonably, you will be getting the full credit. But again, homework is not a big portion of the final grade. So just stick around and see what happens, And I am confident that things will work out. Okay. Exam 1 is going to be on the 22nd, right? Yes, Ronald McDonald team, yes.
For the homework, if we were asked a numerical question, we answered with a number.
Yeah.
Are we allowed to will you give us an approximate answer, or is it just shut?
No. That's as long as you're if you put one significant digit or that's fine if you get the answer, But what I've seen so far, you write the formula correctly, but the answer is not consistent with the formula, right? Okay. So that's a mistake. And if an answer depends on getting the previous answer correctly, what I will tell you is show that A is equal 15, and the next question use A to do something. So if you couldn't show A equal to 15, you lose credit only on that part, right? But then you can use A equal 15. So for questions that are dependent on each other, I will phrase it in a way to give you the answer so that you can use it in subsequent steps, okay? Okay, and so the exam, I posted 4 items in Canvas, a study guide for what to expect in this exam, so no surprises, okay? But as is typical in my classes, I always give a bonus problem in exams, okay? So those could be sometimes worth 50%, okay? Like 50 points. So you can get 150 over 100 if or you don't do one of the main problems and do the bonus problems. But these bonus problems will push you to the extreme, will challenge your knowledge, okay? You don't have to worry about them, but it's an opportunity for you to, yes? Yes. In the exams, you will get partial credit, okay? You will get partial credit. But typically, these bonus problems, it's like if you don't get the first step right, you're not, it's not going to work. So they're difficult by nature. That's why they're called bonus, right? So there's a self-study. Look at the self-study guide. See where your gaps are, okay? And make sure you fill in those gaps. I posted a set of slides that review all what we've done so far. We'll hopefully have time to do it together before the exam. Pardon me. I also posted a practice exam combining problems from the last 3 years. And I also posted a paper by Richard Felder. He's a chemical engineering faculty at North Carolina State University. So he mentored me regarding teaching, teaching methods, etc. So he wrote this really nice paper in chemical engineering education about how to prepare for a test. Okay, so 4 items on your Canvas. Okay, I'm sure you saw the announcement. Make sure you look at those, okay? And you look at those and get ready for the exam, okay? Today we are not gonna solve homework 4. We will do that on Thursday, okay? But we are gonna start a new chapter, okay? And I see a team Professor Saad up there. Cool. Although you misspelled professor, but that's okay. Okay. So today we will start with a new chapter called Least Squares Regression. I'm sure you've heard of the word regression analysis and least squares. So we're gonna understand what those mean in this chapter. The learning objectives for this section, for this chapter, are going to be the following. So the way we formulate these learning objectives, that's also one thing that's going to change in the course is I'm trying to aim at high-level skills rather than just only low-level skills. So low-level critical skills are essentially remembering things. What is the equation of state? So that's just retrieving from memory. High-level skills are creating something, interpreting data, defining, computing things, okay? So we're going to be aiming at high-level skills, and along the way, you'll pick up the low-level skills, but the aim should always be, that's how you develop critical thinking, which is the highest level skill on the scale. Anyway, so at the end of this chapter, you'll be able to do the following. Given a set of observations, you'll be able to compute a best fit curve, that's something that we're going to call a model, that minimizes the error between the model and the observations. And we'll also define what those mean. You'll be able to define linear regression. You'll be able to conduct linear regression for polynomial models. So polynomials include straight lines, right? Because a straight line is a polynomial of degree 1. So you'll be able to conduct linear regression for polynomial models. So again, models are a curve fit to try to interpret the data. We'll see what that means in a second. And certain nonlinear models, you'll be able to define and compute the mean, standard deviation, and standard error. You'll be able to define and compute the R-squared value, create code in Python for linear regression using the derivations we make in class and using built-in tools in Python, both options. And define and use the normal equations to formulate linear regression. Again, this is something that you will learn about. Convert a nonlinear model into a linear regression analysis, and finally formulate the equations for nonlinear regression, which we don't know how to solve yet. Right now, we only know how to solve linear systems of equations. Okay, so today, let me see, get some, oh no, I want more dramatic lighting. Okay, let me see. Oh, okay. So, our chapter begins with a story. Long, long time ago, there was a forensic anthropologist, Bones, as many of you, I'm not sure I can mention her name because, you know, I don't want to be sued, but this is fair use anyway. So, Emily Deschanel, a forensic anthropologist, is called to inspect a burial site. So they discover this burial site, and they find a bunch of bones, and they call her in. Hey, come and have a look. Okay. Now, at the burial site, you know, they find some bones. Most of them are not in good condition. So assume all of these good-looking bones are bad shape, except for that one over there, which is a femur. Okay. So she only finds a few bones to work with, including a femur. Now, this was a top secret, you know, imagine this was a VIP top secret burial site, and she was only given access to the femur, and she was tasked with finding out the height of the individual that was buried in this site, okay? So she was given a femur, and like, figure out the height of the person, among other things, but mostly the height, okay? And the only thing that is known to her is the femur length was 43 centimeters, so about maybe this much, okay? So given that she was a good student and she knows her anthropology, she rushes to her anthropology book and digs up some data because she remembers that there is a relation between femur length and height. Go figure. Apparently, scientists make interesting observations, okay? So there is a relation. There are data that have been collected that relate femur length to height, okay? So she opens up her Jupyter notebook and plots the data, okay? And these are the data. You get femur length on the first column and height on the right column. Now, as far as we know, this data is for mixed gender, mixed race. It's just generic data for a population. Any sample of the population, you know, fits this data. So, and for the femur lengths, you can see 40 centimeters. The height of the individual was 163. You know, 43 centimeters, height of the individual was 67. There's another individual, 43 centimeters was 164 centimeters in height. Anyway, so she does a scatter plot. Okay, for every data point up there, X, Y, she makes the plot. Of course, in Python. Okay. Now, the first thing she does, because it was a morning, she hadn't had her coffee yet, she tried to do, so she wants to predict, so here's the question, she wants to predict the height of the individual given the femur length of 43. So she wants this kind of data point over here. I mean, there's a data point, 43, but there are two data points at 43. Okay, there are two data points, they're here, right? This guy and the guy above it. But, you know, the height of the individual could be anywhere in between. But there's also a lot more data involved. So she wants to use all of these data points to make a good guess about the height of the individual. So first thing she does, like we learned in class, she does linear interpolation. And this is what she gets. So obviously, this is a terrible idea because the data is all over the place. It's a scatter, right? Doesn't follow a straight line or a nice curve. But then, the next order of business, she tries to fit a very high order polynomial throughout the data set. I see Emily, no, bad idea. Indeed, it's a bad idea. In fact, you cannot do it because you have multiple values for the same x value. So for 43, you have 2 data sets. And the polynomial fit is going to say, I can't fit these 2 points at the same time. So literally, the solution for the polynomial does not converge. So you get something crazy like this. So for a person, it tells you for a person with a femur length of 50, their height is going to be like, 3 meters or something. Doesn't make sense at all. But then she says, OK, I'm doing. Hey, guys, do you have a question? Eric, if you have a question, ask me. Otherwise, let's please stick with the lecture. OK. So rather than doing just autonomous things, OK, she says, OK, let me step back for a second. And I'm just going to look at the data. OK? And to me, she says, to her, the data looks like it kind of follows a straight line. So she thinks, I want to draw a straight line between these data, okay? So now my question to you as groups, and you have 30 seconds to answer this question. Given what you know so far about numerical methods, interpolation, etc., is this doable? Go, 30 seconds. I want to hear noise.
Yes. It is. Why?
Okay, time. All right. We'll start with a funny name. We have here Team Dumpy. Okay, so all right. Who is the speaker for the group? Who can? What do you guys reach? What thoughts? Can you put a straight line through this entire data set? So let me show you the data set again.
I don't know how to do it, but I know it's possible.
Okay. That's a reasonable question. But given what you know about numerical methods, storm crows, let's say, yeah. Given what you know about interpolation.
We said that based on the methods that you've taught us so far, there isn't a way we can have a perfectly straight line. But
Why? Why?
Because it requires you to take the average distance between all the points and
Before you get there, you're getting ahead. Yes. So yes, but we can't fit a straight line. Why? Do I have any volunteers? Okay. So if no volunteers, I'll pick Pietra. So a straight line. What does it need? How many points do you fit in a straight line? 2 points. Not like just 2 points. Yeah. You got it. So obviously, based on what we know about numerical methods, we cannot put a straight line through in more than 2 data points at a time. So there's no way we know so far how to put a straight line, draw a straight line in this data. But we're going to learn to do this. Rather than doing it exactly, we're going to get a sense of capturing the trend of the data. And that's what regression does. So given that Bones, having taken numerical methods, the University of Utah, she does what's called linear regression. And linear regression, so I'm going to give you the solution first, and then we'll dig deep. With linear regression, she can find a formula for a model that she thinks works for the data. Her model for the data is a straight line, and she wants to find that straight line that best fits these data points. The meaning of best fits, we're going to define it later. But roughly, it's going to minimize the error or the distance between the straight line and the data points. This is a unique solution. This is the only straight line that minimizes what we call the least squares error. Okay? We will define that also later. But this is the formula of the straight line. It's 1.0043x plus 123.21 for these data points, okay? And then she estimates the height of the individual as 166.39 centimeters. Okay. Now we can dig into the basic idea of regression. Okay. And again, we're going to take a set of data points that follow a trend, but they're not the trend is not clear. But there is a trend, but it's not like just all a straight line or a curve. They're all over the place. They're scattered, right? But there's a sense of the data. Like these data points, they kind of follow a line, right? They follow a direction. And that's understandable because in nature, rarely do we get kind of exact observations that fit nicely through a nice curve, right? Beyond theoretical investigations, in practice, you don't get very nice curves. So you're going to get scatters. Okay? So let's call these the input data points. And let's say you want to fit a model curve. And when I say model curve, that could be, we will show, that could be anything you want. You can come up with the formula of what you want your model to look like. In this case, we're going to do a straight line because it's easier to start dealing with straight lines. But later on, we're going to move to polynomials and exponentials. But early on, we're just going to say, OK, these data look like they fall or follow a straight line. So let's draw a straight line, and we'll call this a model curve. That's the model of our data. What is a model? A model is something that represents reality. Okay? Now, notice that there's a distance between the straight line and the observations, correct? So the straight line doesn't go, or this curve, let's call it curve, not to focus on straight line, does not go through each and every individual point. There's a distance. And that distance is an error, correct? That's the error between your model and your input data. For each input data point and your model is going to tell you at this x, your model gives you this value, but your observation gives you that value. Okay? So there is an error over here between the two. Okay? Now the question is, the basic idea of regression answers the following question. Find the model curve that minimizes the error between all of these points. Okay? So let's start by doing a concrete example. I'm going to take 3 data points from the data set I just showed, x and y. X is the femur length, 40, 41, and 43 centimeters, and y is the height of the individual, 163, 165, and 167 centimeters. And I want to fit a model that's a straight line. The equation for straight line is ax plus b, or a1x plus a0 to simplify the nomenclature. Okay? Now notice I call this y model, and I define it as f of x, because I want to reserve the symbol y for the input data, okay? For the input y values. So from here onwards, we're going to call the modeled values as f of xi, or f of x, okay? So now we go back to our original question. How can we fit a straight line, which has 2 unknowns, right? So a straight line, ax plus a1x plus a naught. X is known because that is the height of that's the length of the femur. So I want to give my model the length of the femur, and I want it to give me the height. So I know x, but I don't know the coefficients, a1 and a naught. Okay? So I'm stressing this out so that you don't confuse the nomenclature of what x and y mean. Okay? So over here, the unknowns are a1 and a naught. Okay? So obviously, we cannot do this, right? That's why we're going to do regression. So here's another graph illustrating my model fit through these red points and the observations that are shown in disks. Okay? And this is my model. Now, for simplicity, I want to call the function evaluation, or the model evaluated at point x, I'm going to call it fi. So when I take my model and evaluate it at one of the input data points, so in this case, first point is 40, second point 41, third point is 43. When I apply the model at that point, I'm going to call the value, that value in red, I'm going to call that value fi, to distinguish it from yi, which was the input value. And this is critical, okay? So I define fi as f of xi, and that's the model applied at xi. Agreed? All I did was take this model and apply it at the input values. Okay? And I'm going to call this fi. We still don't know what a1 and a0 are. And this is to strengthen the nomenclature, the idea that the f's correspond to the model value at the input x values. Okay? The model y values at the input x values. And the y's, there's y1, y2, and y3. Those are the data that are given to us. Okay? So fi denote model values, and yi denote input values. Okay. So obviously, we know that we cannot fit a straight line with 3 data points. Now, the idea to circumvent this problem, and you'll understand why this circumvents this issue. So the problem here, again, to reiterate, we have only 2 unknowns, but we need 2 equations. But which 2 data points do we choose to fit the straight line through? You have more equations than unknowns, right? So in this case, you would have 3 equations and 2 unknowns. Or if you had 100 data points, you would have 100 equations, but only 2 unknowns. So the system is overdetermined. Okay, there's no unique solution. Obviously, we don't want that. Now, one idea to circumvent this problem, and you will understand why once we derive it, is to minimize the error between fi and yi. So in other words, like I said earlier, obviously, the model curve does not go through the data points, the observations. Okay? There's a difference. There's an error. So why don't we find the slope and the intercept of that line such that this line is minimizes the total error across the entire data set? Now, that means we need to define what the total error is. One measure of the error is the sum of the squares of the errors. So bear with me for a second. What is the error for each data point? The error for each data point is y1 minus f1. Okay? For the second data point, it's y2 minus f2. And for the third data point is y3 minus f3. Agreed? Okay. Now, if you take the square of each one of those values and sum them up, that gives you a sense of the global error in your data. So in other words, if I take y1 minus f1 squared and add it to y2 minus f2 squared and add it to y3 minus f3 squared, yes, Eric?
So why do you use squared instead of just the absolute value?
Because the absolute value is going to cause troubles. I'll send you a document after the lecture. There are other measures of error that do not quite work as well as the least squares, as the square of the error. So there's a reason we do the squares. And I'll send you documentation on that. I'm not going to cover it in class because it's a major diversion, but I'll send you the documentation on that. Good, very good question. Okay. So now if you stick with the idea of the square of the errors, like I said, the sum of the square of these errors is a measure of the error. And you can define this error the way you like. I mean, you can try doing the absolute value, but it doesn't work on all types of data sets. There are other measures of error, but this is the most common measure of error. Okay? It's called the sum of the squares of the error. Okay? Now, our question is, okay, so we have y1 minus f1 squared plus y2 plus y3 minus f3 squared. But fi is a1 xi plus a naught, correct? So now take up a sheet and fill in the blanks for s. Okay? Grab a sheet of paper or your notebook and whatever, work in groups, and let's fill out what s is. Okay? You have a minute, so I want you to substitute f1, f2, and f3 in the formulation for s. Okay? Right? Yes?
So does this have to do with anything with Pythagoras? Fits really well.
No, it's just a measure. I mean, yeah, it's a Pythagorean norm with the sum of the squares. But I mean, you can pick another norm, right, for the error. You can pick, like he said, the absolute value. But I think, yeah, I don't know. I mean, you can't say it works well. I mean, again, you're optimizing based on what error you choose, right? But it's just a very common measure, the squares of the error. It's just because it works for pretty much all data sets. You know, it doesn't cause any problems. Okay. Okay. So you know what you're doing. You know what F is. So we want to plug that in S, okay? I'll give you an extra 30 seconds. Just substitute. Back corner. I love your team.
No, yeah, in the first A, but the A naught should stay the same. So A1 and A naught.
Yes.
So question.
Yeah.
A naught doesn't change for each one because it's not an iterative verb. Where did A naught come from? Is it just
We don't know what A naught is. Our goal is to find A naught and A1. But right now we're defining the error in terms of A naught and A1.
correct? But
And then we're going to do something with the error,
okay.
okay, to minimize it.
Is it an optimization?
Yes, it's an optimization. Yes, yes. Okay. Okay. Time? All right. So, are you guys are working in a team? Yeah. All right. Isabel, do you want to take the lead? Okay. Yes, yes. So did you try to do this by hand? Do you have a? Yes. Okay. So what you do is simply take F1 and say this is A1 X1 plus A naught, put it up in S, and then take F2 and F3 and put it up there. We still don't know what, so this is the result if you want to compare to your values, okay? All we did here was substitute our model form into the error, a definition of the error. So step back for a second. We started out by saying we cannot fit a straight line of the form A1x plus A naught into all of these data points. Instead, we're going to fit a line that minimizes the error. But first, we need to define the error. So we define the error as a function of the model and the input data points. Then we substituted the model form into the error. Now notice A1 and A naught, they're still unknown, shown in red here, okay? And they will still be the same. It's A naught and A1, they're the same for F1, F2, and F3, but only X1 and X2 and X3 shows up. Okay, so now we expressed our error in terms of our model. That's a very important step, okay? So now, we still have one more step. We said that we want to find the curve that minimizes the error between the curve and the observations. We have the error. We still want one more step. We want to minimize this error. So when you look at S, y1 and x1 are known quantities, and y2 and x2 and y3 and x3. The only two unknowns are A naught and A1. Okay? Now, when is a curve minimum or a max? Yes? When its derivative is 0. Okay? So, for a single function, okay, for a single valued function like f of x, the derivative is a minimum when the function is a minimum when the first derivative is 0. Okay, minimum or maximum. Okay, when the first derivative is 0. Okay? Same thing applies here. Now think of S as a function of two variables, A naught and A1. The same idea applies. This function S of A naught and A1 is a minimum if and only if its derivatives with respect to both unknowns are 0. So the only step, the only extension of knowledge we did here is say we went from 1D, where we had only f of x, a function is a minimum or maximum when the derivative with respect to x is 0. We just went to 2 dimensions. Now we have A naught and A1 as our unknowns. And S is a minimum. We can show that this is a minimum, actually, when ds by dA naught is 0 and ds by dA1 is 0. This is a partial derivative. Okay, so the partial derivative works by you hold everything else constant and you just do regular differentiation with respect to the variable in the denominator. Okay, all right, teams, you have 2 minutes now to fill in the blanks. I want you to derive the formulas for ds by dA naught and ds by dA1. Okay, now let me give you a hint. 1 second. I'll give you a hint. Okay? The derivative of, hold on. Okay, remember the derivative of u to the n is n u prime un minus 1. Okay? So you want to differentiate with respect to a naught and differentiate with respect to a1. How do you differentiate with respect to a naught? You assume everything else is constant. Yes?
That's A1 is the only non-constant. Everything else is constant. So
Depends.
A1s are variable.
A1 and A naught are unknowns. They're variable. We don't know what they are. We're trying to find them. But when you do ds by dA naught, so why don't you guys work together, please? Otherwise, I'll assign you other groups. Just get to working together, please. I know you know how to do it, but sharing is will be helpful to everyone. Okay. So when you do the derivative with respect to A naught, you hold everything else constant except A naught, and you treat it just as a regular derivative. Okay. Jeff, why are you working by yourself? Oh, you're working with me. Okay. Okay. Full awkward. You should move back there. Yeah.
This one, we'll take the derivative.
Ryan, Team Chocolate Bin. Team Chocolate, you didn't have it. Team Chocolate Bin, yeah. Well, you get some extra then. Yeah. How's Team Saad doing?
So it's really only one F? Are you serious?
Yep.
It's more Fs than I need.
Okay, 30 more seconds. No team name?
Oh, we didn't put a paper. Our team
I don't know. Okay, so let me get you a sheet of paper. And I'm missing my 3 markers, red, blue, and black. Oh, we consumed the entire document. Oh, thank you. Thanks. Okay, time? All right, Connor. Yes. So tell us about the derivatives.
Okay, so the derivatives are found by you gotta take the derivative, and we have to use the chain rule in order to do that.
The chain rule. Why do you need to use the chain rule?
Because
Yeah.
you can't just take out that one little A naught and do the derivative of that A naught. You have to do the
You can.
parentheses.
Yeah, you can, but you do it at the bottom. So we
the
have
chain rule.
Brandon had a, yeah. Okay, you're good. You don't wanna take it. Okay, so let's see. IDK over there. Brian, do you wanna? Yeah. Do you wanna go write it on the board? Yeah. Okay. Here's a marker.
Ryan, do it gross, so just foil everything out.
Let's do ds by dA naught and explain as you do it, please.
So
Oh, it's not working.
No.
Let me give you another one. Try this one.
Okay.
Okay. If you can't see his handwriting,
So first we have our function, which is like this.
y1 minus a1 x1 minus a naught squared.
And then
Okay. So why don't you just do the first term?
just the first
Because the rest will be the same, right?
Okay, so first
Yeah.
we start.
So ds by dA0 for this guy. Yeah.
So you take the exponent, put it in front,
Uh-huh.
and then that's the first part of it. And then right here we have the negative we take the derivative of
Uh-huh.
the a naught
Uh-huh.
inside by itself, which is just
Okay.
-1. So then it becomes -2 times y1 minus a1 x1 minus a naught.
Okay. Okay. Very good. Thank you very much. And the same thing applies for the other one. So let me elaborate. Marker? Did you? Oh, put it over there. Okay. So there's no eraser over here. There's no chalk either. So like Ryan said, and what Connor said too, the variation of the chain rule is essentially you treat every one of those terms as a function. When you differentiate with respect to a0, you hold everything else constant and you differentiate with respect to a0. So the first term, think of it as u to the n, or u squared. You're taking the derivative of that. The derivative of that is n, which is 2, times u prime, the derivative of this entire thing in parentheses with respect to a naught. And that is -1, right? Because d minus a naught by dA naught is -1, times u, the original function, to the power n minus 1. Now, let me show you the answer, if my computer works. Okay. Okay. So this is what you get. Okay. Just two formulas, okay, with a naught and a1. You know, the pattern looks the same. We'll simplify it once we generalize. But the point is here is that as you arrange terms together, can you make an observation? Academic masochism. Can you make an observation here? So start with the model curve. What were we after with the model curve? Let me simplify the lighting for you. So we were looking for a naught and a1. Okay? We're looking for a naught and a1. And we need to find these two unknowns. We need two equations. How many equations do we have? We have two equations and two unknowns. Yay! But not only that, these two equations, they are derived in such a way that they minimize the error, right? Because they were derived from ds by dA naught equals 0 and ds by dA1 equal to 0. So my claim, yes? Yeah, that's what we did. We found the point where the derivative. So in other words, what we're saying, find a naught and a1 such that these equations are satisfied. And if these equations are satisfied, they minimize the error because these equations were derived from minimizing the error, right? So if you start from the end, that's what we're after. So we're going to find the line. If we find a naught and a1, that means we found that straight line. But if we find them from these equations, we are guaranteed that we will minimize the error. Okay, so we have two equations and two unknowns. I'll give you a break now. Okay, 3 minutes. All right, or 3 minutes. Okay, go drink some water, and then we'll continue. I know you've been like so engaged. Emily is like, no, don't stop. But okay, there's a lot more to come. Record. So the derivative of a function u of x, we typically use x as the unknown, to the power n. So if you want to differentiate that with respect to x, the solution is n du by dx times u to the power n minus 1. Okay? And I call this u prime, so n u prime un minus 1. Okay? So if you had x squared, you would do n, which is 2, times du by dx, that's dx by dx, which is 1, right? Because in this case, u is equal to x. So dx by dx times u to the n minus 1. So that's x to the power 2 minus 1. So that gives you 2x. That's where that formula comes from. Okay, and remember when Emily gave me when I spilled coffee on my laptop, I still have some of those paper napkins. So I'm using them to erase. Okay. So now what if you had something like 1 plus x squared? Then this is your u. U is equal 1 plus x. So then the derivative of this would be n, so that's 2, times du by dx, so that's d of 1 plus x by dx, times un minus 1, that's 1 plus x, u to the n minus 1, 2 minus 1. Okay? Now let's do 3. Okay? So you'll get 3 times d 1 plus x by dx times 1 plus x to the n minus 1. So that gives you 3. Now d1 plus x by dx is what? 1 times 1 times 1 plus x squared. Same thing applies here. Okay? Let me keep these guys. Maybe I'll write it over here, right here in the corner. So for our case, although this is partial derivative stuff, it's still not that complicated. We can treat it as a single function. So in our case, we have s has a bunch of terms. One representative term is y1 minus a1 x1 minus a naught squared. Now when I'm doing ds by dA naught, everything beyond a naught is a constant. Everything other than a naught is a constant. Okay, just like the one over here. So ds by dA naught, essentially if you call your u function as y1 minus a1 x1 minus a naught, u is a function of a naught now. Okay, so we're only differentiating with respect to a naught. Then you get n, which is 2, times du by dA naught, okay, times u to the n minus 1. So you get 2 times, what is du by dA naught? This is u. What is du by dA naught? Pardon me? Minus 1 times minus 1 times u to the n minus 1. So that's y1 minus a1 x1 minus a naught to the power 2 minus 1, which is 1. You do the same for all the other terms. Same thing applies for a1. a1 is a little bit more interesting because a1 multiplies x. Okay? So let's look at ds by dA1. Now our u is a function of a1, ua1. Okay? So we hold everything beside a1 constant. Okay? So ds by dA1 would be equal to n, so that's 2, times, I can't reach it, it fell down. We need another marker. Okay, ds by dA1 is 2 times du by dA1 times u to the power n minus 1. Okay, so that's 2. Now what is du by dA1? Okay, du by dA1, we hold everything else constant except for a1. What is du by dA1 is minus x1 times minus x1 times y1 minus a1 x1 minus a naught to the power 2 minus 1, which is 1. Okay? And that's how you get the negative 2x1 over here. Okay? Okay. So now we did this for 3 data points because, you know, I like to learn in this manner, start from, you know, simple concepts and then generalize. Obviously, we need to apply this to an arbitrary number of observations, okay? So we look at the general form for a straight line linear regression. Our Y model is still A1x plus A naught, but we could have 10, 50, or 1,000 data points, or 1,000,000, it doesn't matter, and data points, okay? So again, the question, how can we fit a straight line with 2 unknowns into n data points? And this is the example we used. Again, we define fi as the value of the model function at observation xi. And that gives us, you know, fi is a1xi plus a naught. We did this. If we minimize now the error between fi and yi, we're obviously going to get more terms in the expression for the error. Previously, when we had 3 points, we only got 3 terms, right? y1 minus f1 squared plus y2 minus f2 squared, and so on. In this case, you have n observations. So you're going to have n of these terms, okay? To simplify things, I'm going to write this as a summation. So S is now written as the sum of yi minus fi squared. Yi is the observation. Fi is going to be our model applied at xi, okay? So yi, you take all the y values you observed. Fi is the model applied at all the x values in your observation. Difference squared. The summation runs from 1 to n, okay, over all the data points, okay? So now we do the same thing. We take fi as a1xi plus a naught, agreed? And we substitute, just like we did before. Okay? Now we have a very large formula for the error, S. But how many unknowns does S contain? 2 unknowns. It contains 2 unknowns, a naught and a1. Looks like I have a lot of volunteers. That's good when I ask a question. No need to ask you to group up to answer questions. Okay. So now S still looks the same as before, except we have more terms in it. N terms, okay? And again, S is minimum if ds by dA naught is equal to 0, and ds by dA1 is equal to 0. Okay. Now the next activity, I want you to really pull your strengths together as a team. I want you to derive these conditions for this general case. And I want you to write the answer in terms of summations, okay? You got 3 minutes. All right? Go. So start by writing down the summation. Differentiate with respect to A naught. Differentiate with respect to A1. This is honestly simpler because it's one term. So it would be best if someone records and the other team, you know, talks to the recorder. Tired triad. I just noticed the sad. I just noticed that. Oh man, you misspelled on purpose. It's not going to help you if you look at the answer. It's not going to help you. It's not going to help you if you look at the answer. Oh, sweet. Man, I want you. I'm taking this.
Now you always remember.
Bark.
That's right. You gotta be able to read
Barak. Is that how you pronounce your name? Barak?
Like Derek.
Yeah,
Yeah,
Barak.
it's kind of
Barak.
your name, but
That's really cool, man. Love the art. Yeah. Bug zappers. Okay, how we doing, bug zappers? You got it. Okay, very nice. So you got 1 minute. Hypothetically.
Trying to figure out how you do the second word.
Very nice. That's gonna be next. Yeah, yeah. How we doing, storm crows? Doing well. Yeah. Look at that. All right. Good job. Good job. Very nice. Very nice. Okay. Yes. So before we, like 10 seconds.
I had like homework 5.
So yeah, we
Just-
thought
just this.
let's.
Is that okay?
Yeah. Let's talk about after class, please. Okay. 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 Time. All right. So we got the bug zappers who are gonna volunteer. Bug zappers. Katie, would you like to volunteer your answer? Do you want to go up the board and write it, please? Yeah. So in many ways, this is simpler because you just have one term that you're differentiating. The summation is not going to make a difference, okay? So do the first one, Katie, and then we'll ask someone else to do the second. Let me erase this for you. So just use the S on the slides. Just write ds by dA naught, and talk to us along the way.
Okay. Well,
Wow, that's a great font size. No, I should aim at this font size. Okay, so the summation remains. Yep.
we just use the chain rule to do
the first one. So you get.
Put the -2 out front, and then we
Okay.
put everything the same side.
Yep. Because that's n times u prime, which is -1 because we differentiate with respect to a naught. Okay, times un minus 1. Great. Thank you, bug zapper. Okay. All right. So for ds by dA1, we got the back corner. Do you have a solution back corner? Okay. Maddie is gonna share with us ds by dA1. So the difference with the second the difference in this term is that a1 is multiplied by xi. So we're going to have an xi involved. Also very good font size. -2 summation, okay? So n times u prime times un minus 1. The negative sign comes from u prime, from the derivative with respect to a1. So what is the derivative of what's inside the parentheses? What's the derivative with respect to a1? Is minus xi. That's where the negative sign comes in. Thank you very much, Maddie. Uh-oh. I have two pens in there. Okay, no more writing on the board. If anyone has long, thin, okay. Okay, thank you. Okay, so that's right. And notice how Maddie wrote it. She immediately pulled the 2 outside the summation because 2 is a constant, okay? Both answers are correct, all right? So compare your notes. This is what these 2 equations tell us. Now, there's still 2 equations and 2 unknowns. And if we solve for A0 and A1, what is that going to guarantee to us, Andy? If we solve for them, that's going to guarantee that the error is minimum. The error as we defined it is minimum. Because that's how we derive the equations for A0 and A1. Okay? Once we have A0 and A1, we're going to have a straight line that is guaranteed to minimize the error. Okay. So now, I'm just going to do some bookkeeping because I like to write, to consolidate terms together. I want to write this as a system of equations with the left-hand side and right-hand side, okay? So let's go ahead and do this. I'm going to split the summation for simplicity. So first, I'm going to cancel out divide by minus 2 on both sides because, you have 0 on the right-hand side, so you get rid of the minus 2. And then you get sum yi minus a1 sum xi minus sum a0, okay? And sum xiyi minus a1 sum xi squared, right? Because we multiply xi by xi, minus a0 sum xi, okay? That's just splitting the summations. Now note one thing is that sum a0 is n times a0 because we're summing over the number of observations. So in other words, we're summing a0 n times, right? So summation of a0 is going to be equal to n times a0. That's the only change I made here, okay? Okay. Now what I want you to do, yes, Andy.
Are we ignoring the -2?
So the right-hand side is 0, right? So you divide by minus 2 on both sides, you get rid of the minus 2. Okay? Okay, now this next activity, you have to do it individually. You have 1 minute to do it by yourselves, no talking. And then you group together and come up with a unified answer for the group. So you have 2 minutes. First minute, you do it yourself. Next minute, you find among each other to get the right answer, okay? Go. What I want you to do is write this system in matrix form. AX equal B. X, what is X? It's not X, it's A0 and A1, right? But I want you to write it in the form matrix times unknown vector equal something. All right? Got 2 minutes. Yes. So I want you, yeah.
Can summations go on the inside of a matrix as well?
It doesn't matter. So this summation is a number. Sum xi is just a single value, right? Because xi are known quantities. So just write this in, AX in the form coefficient matrix times vector equal B. So do it individually, please. First by yourselves, and then argue amongst each other. If you need a sheet of paper and a pen, I'm happy to give you one. You agree that this is a system of equations, 2 equations and 2 unknowns. I just want you to write it in matrix form. Okay, you should be talking to each other now. Yep. Yep. Yep.
Where does the n come from?
So you sum a naught n times, right? So that's n times a naught, right? Because you may be tempted to take a. Okay, time. All right. So, all right. Let's start with Henry and Professor Saad team, or whoever wants to speak for the team. Do you wanna? Yeah. Do you just tell us, kind of conceptually? Yeah, guys. If you have a question, just let me know, please.
We're discussing still. You told us to
I said time just a second ago.
like 1 minute to do it on our own first.
Yeah, you had 3.5 minutes actually passed. So, okay. Do you wanna go up the board and do it? Yeah. And there is a cell phone over here.
We just found it from the last class.
Okay. So we'll make sure to give it to Tina. Okay. So we got almost 5 minutes left. Okay. Squared. Okay. Okay, so I disagree with this answer. Okay, because this is not consistent with the system of equations.
Oh, am I missing the y here?
Still, this is not consistent because this matrix is not 2 by 2. This is 2 by 3.
Yeah.
Right? Times 1 by 2, which was times 2 by 1.
Yeah.
Okay, which is not going to work. You can't do the product with these guys.
Yeah.
Okay? So this is an incorrect answer. We got some volunteers. Natalie. Yeah, just say it. Yeah, okay. So what the numerical migraines team is saying is that they moved all the coefficients that don't have red in them. So all the terms that don't have red, the sum yi and the sum xi yi, they moved them to the right-hand side because those are known quantities, right? So that's like saying, I'm writing ax plus by equal 3, okay? So they moved those terms to the right-hand side and rearranged it in that way. So let me show you. Okay? So first equation, I multiply by a negative sign everywhere. I move sum yi. So that gives me a naught times n plus a1 times sum xi plus equals sum yi. Same thing at the bottom. We move sum xi yi. It's a known quantity. Remember, all the xi's and the yi's are known values. Okay? All the xi's and yi's are known values. All right, so what we're looking after are a naught and a1. Okay, and then naturally, the matrix form emerges from this, in the coefficient matrix being, so it's nothing more than rewriting the equation. The first row in the matrix are the coefficients of the unknowns in the first equation. Those are n and sum xi, and your solution vector, your unknown vector, is a naught and a1. So in other words, this equation produces the dot product of n sum xi with a naught a1. Gives you n a naught and sum xi times a1, which is the first equation equals sum yi. Same thing at the bottom. Now, that's a system of linear equations. And we know how to solve systems of equations, right? And this is a pretty benign system. It's 2 by 2. You probably know how to solve it analytically as well. But I'll give you the answer. But we can plug this into Python and just do a direct solve, right? Because it's a small system. And turns out that this is the answer. And so for our problem, this is what we get. Now, before you leave, okay, I want a couple of volunteers to come measure your femurs. So we can predict your height. Of course, Katrina. All right, Connor. Okay. All right. So the bottom, this is in centimeters. So I want the number in centimeters. Yes, please. Okay.
Where do you measure?
No, the femur. So from your, yeah.
I know, I took anatomy.
She took anatomy.
Got my tibia and my fibula. It's fine, whatever. This is embarrassing. It's fine. I was. That's far off my head now.
Okay, so what was Katrina's?
Like 40?
Okay, 40 centimeters. Okay, let's plug in the numbers. 1.0043 times x plus
I'm not pretty good.
123.21. So it gave us a prediction of 163.382 centimeters.
44. Yeah, 44.
5 foot, like 2?
Okay.
1.5 more like?
Okay. Well, you verify if there's an error or not. What about you?
44 centimeters.
Okay.
I also got 44 centimeters.
Hey, let's go.
Okay, gave us 167.4.
What is that?
And so 167.42 feet. So like, geez, what is? So it's like 5.4 feet.
5.4.
You're probably tall. Yeah, you're probably about that. You're probably 5.6. Yeah. So mine, I'm about 5.6, 5.7. So I got 40 centimeters as well. So obviously there's an error. Next week we'll talk about that error. Okay? Next week we'll talk about the error. Thank you very much. Okay.